Okay. Ready to go?
Yeah, good.
Okay, well, it's my pleasure to welcome Julie Hlavacek Larrondo from the University of Montreal. I've known Julie for quite a long time. In fact, since she was at Cambridge studying with Andy Fabian for her PhD. She finished her PhD sometime around about 2012. I don't know all the dates, but it'll be roughly right. She finished her PhD and then went off to with Andy, studying galaxy clusters, particularly focusing on distant galaxy clusters and how they evolve. She then went off to Stanford to do a postdoc. She was an Einstein Fellow there in Steve Allen's group at Stanford. And after a few years at Stanford, she was offered a faculty job at Montreal, where she's been for the last, I think, 6 years. She's a Canada Research Chair at Montreal and has done some very significant work on the evolution of galaxy clusters, focusing on feedback from the central galaxy, the growth of supermassive black holes, and so on. So Julie today is going to tell us about black hole feedback and galaxy clusters, and I'm looking forward to hearing your results. So take it away.
Perfect. Thank you so much, Brian. So first, I wanted to thank you, thank everybody for inviting me. I would have loved to be there in person, but my youngest brought back the stomach flu from daycare and generously gave it to the whole family. So I could not be there in person. But I'm very happy to talk to you today about some new results that we've obtained on black hole feedback in galaxy clusters. So the goal of my work has really been to study supermassive black holes and understand how these black holes feed back energy into their surroundings. And as we'll see, supermassive black holes do much more than just heat. It turns out that they play a profound and dominant role in shaping many of the properties of galaxies throughout time. And that's one of the topics that we'll show today. Okay, so let's get started. So we're pretty sure that essentially every massive galaxy in the universe has a supermassive black hole at its core. But here's the catch about these black holes, and this is what makes them really so fascinating. Supermassive black holes, although very massive, they're actually very compact. So the event horizon of these black holes is typically about 1 million to 1 billion times smaller than their galaxy. And so the first question that you can ask yourself is, can something that is so tiny actually have an impact on the scale of a galaxy? It's kind of like saying, can my cell phone actually do something on the scale of the Earth? So it turns out that the answer is yes, and this is really what makes black holes so interesting. So you can do this kind of calculation to see, just how much of an impact a black hole can have on its galaxy. And you can take an example here. So this is calculating the energy that's typically associated with black holes. A supermassive black hole will have accreted, let's say, about 10 to the 8 solar masses throughout its lifetime. And so it can feed back about 10% of that energy into its surrounding. And if you do that calculation, you get this typical number here. And then you can compare this to the actual energy it would take to unbind an entire galaxy. And so what we're calculating here is the binding energy, specifically near the central regions, let's say the bulge of the galaxy. A typical bulge will contain about 10 to the 11 solar masses in material. And then compared to the speed of the stars, you can get an estimate of just how much energy you would need to feed back into this galaxy to unbind it. And this is the kind of number that you would get for a typical galaxy. So you can see that black holes can easily have enough energy to really have an important and significant impact on their galaxy. So thankfully, black holes don't just destroy galaxies. They have a much more gentler way of impacting the galaxy. And this is what we're going to see today. So typically, when we talk about black hole feedback, there are 2 different modes in which the black hole can operate. Either the black hole is accreting at very high rates, typically above 1% of Eddington. And in this case, the black hole goes into what we call the quasar mode. And you have the black hole that's secreting a lot of material, and most of the energy that's going to be fed back will be in the form of radiation and winds in this case. Now, the downside about this mode is that it's actually it doesn't happen often that the black hole can accrete this much material. It will go through these phases in its lifetime, but not very often. On the other hand, when the black hole accretes at very low rates, so typically 1% of Eddington or below, then it goes into this jet mode. So it's much more likely that the black hole will be in this mode because it doesn't require that much material to be in that mode. And when this happens, what happens is that the black hole, the accretion disk changes, the physics in the accretion disk changes, and it becomes very easy for the black hole to form radio jets. And this is why we call this radio mode or maintenance mode or mechanical mode. So essentially the black hole will have a radio jet in this mode. And it turns out that galaxy clusters are really fantastic places where we can witness this kind of feedback, this jet mode feedback, and see what radio jets are actually doing to their surrounding medium. And this is why we use galaxy clusters to understand black hole feedback, in particular in radio mode. And so this is an example here. It's a classic example called the Perseus cluster of galaxies, one of the most nearby clusters. And what you see typically at the center of a cluster is its dominant galaxy. So this is the galaxy that dominates in mass and size. It's a huge galaxy. It's very old as well. It's taken a long time to form. As a comparison, up here on the top left, you have the size of the Milky Way. So these galaxies are really much bigger. And these galaxies also harbor a black hole, a supermassive black hole at its center. This black hole is going to be in radio mode, so accreting at less than 1% of Eddington, and it's going to be driving radio jets. And this is what these radio jets look like typically. So what you see in pink here is VLA observations that trace the radio emission of these radio jets, which is essentially due to synchrotron emission. And so typically, if you have a galaxy and you see these radio jets, you see that the black hole is in radio mode. But if this galaxy is outside of a cluster, then we wouldn't actually understand or see what these jets are actually doing to their environment, how they're impacting their environment. But thankfully in galaxy clusters, and this is the great advantage of them, is that we can actually see the gas that's around galaxies. So the gas that surrounds the central galaxy and the gas that's essentially filling the cluster of galaxies. This type of material is called the hot intracluster medium. So it's made of essentially a lot of gas that you find between the galaxies of the galaxy cluster. And because of the deep potential well of galaxy clusters, these are very massive structures. They contain hundreds to thousands of galaxies, a lot of dark matter. Then any gas that falls into this deep potential well will feel the energy of that potential well and will get heated. And you can do the calculations and you see that for such a massive structure, a deep potential well, the gas gets heated to about 10 to the 7, 10 to the 8 Kelvin. So very, very hot. And when gas is this hot, it emits a lot of X-ray emission. And so what does this actually look like? So we can take an X-ray image of this gas, and this is what it looks like. So what you see here is the same image. So you have the central galaxy that harbors a supermassive black hole in radio mode feedback. It's creating these radio jets. And surrounding in blue, you have the hot intracluster medium that surrounds the central galaxy here. And this is what we see through X-rays. So the key advantage here is that since we can actually see the environment around the galaxy, we can see what the radio jet is doing to this gas. And as you can see, what happens is that these radio jets, as they propagate, they are literally pushing away the hot X-ray gas. They are carving out what we call cavities, and they're actually doing mechanical work to push away the gas. And the typical example that I like to give is in Canada, we have a lot of snow. So imagine when you have to shovel out the snow from your driveway. Well, it takes a lot of energy to push away that snow. It's the same thing happening here, except in this case, we have a single object at the center, which is tiny in size, but so powerful that they can sweep away gas on the scale of an entire galaxy. And so you can imagine that it takes a lot of energy to be able to do that and push away that kind of gas on that kind of scale. Once these cavities form, what happens is that they act like bubbles of air in water, and they literally detach and float to less denser regions. And you have one example here of an old cavity which has risen buoyantly. Same thing here to the south. And so they really act and are governed by the same kind of physics as air bubbles in water, although on astronomical scale. So it's super interesting to see that the same kind of physics applies. So this is why we use galaxy clusters. If you had the exact same galaxy, but was located outside of a cluster, you would see the radio jets. But the material that's around the galaxy is too diffuse to be able to see with current telescopes. So you wouldn't actually see what those radio jets are doing to the surrounding gas. Here we can see this gas very well through X-rays. And so we've been studying these galaxy clusters and studying the radio mode feedback properties. And essentially what kind of like a summary of what we found, what do black hole jets actually do to galaxies? So we see this radio mode feedback happening in clusters, in groups, and some isolated galaxies, which are massive enough where you can actually see the gas that surrounds the galaxy and see how this black hole jet is impacting this gas. And what studies have shown is that these kind of outflows, these jetted outflows, are super energetic. They have a lot of power to be able to sweep away all of this gas and material out of its way. Here are the typical energies associated with these outflows. These numbers might not mean much, but essentially what this kind of number gives you is that radio jets are able to really have an important role. And what happens is that these radio jets are going to inject energy into their surrounding, and the kinds of energies are enough to keep the hot X-ray gas hot and prevent it from cooling and forming stars. Without radio jets, all of this hot X-ray gas would cool and would form massive starbursts. So it's suppressing the star formation rates by orders of magnitude, not just a little bit, but really by orders of magnitude. And so it's having a profound impact on these systems. The second question that we can ask ourselves is, besides the energetics, so we see that there's a lot of energy in this kind of radio mode feedback, how is the energy actually distributed to larger radii? So the example that I like to give is, if you have a balloon in let's say in a classroom, and you inflate this balloon, this balloon is going to displace the air around it, but it's not actually going to heat the room. And so how does this black hole and these radio jets actually heat and transfer energy at larger distances? It's still a question that's debated, but we do see some evidence of shock fronts that surround these radio jets. When we do see them, they tend to be very low Mach numbers, but they can still be very powerful, even with those kinds of Mach numbers. So this would be one way of heating the environment. There's also been a lot of work that has found evidence of either sound waves that are being generated by these outflows, or turbulence that's being generated from these outflows. And this turbulence could then heat the surrounding medium. So those are other ways that these radio jets can do this. Another really interesting result that's come out in the last couple of years, and this has been led a lot by Brian and his team, has been the discovery that radio jets don't just heat the surrounding gas, they can actually drag out metals from the inner regions of the galaxies to very large radii. So they can drag this material, this metal-rich material, and deposit it to large radii. They can also, it appears, to drive very massive molecular outflows on the scale of a galaxy. And so these outflows are typically a couple hundred kilometers per second, contain a lot of molecular mass, And this is very similar to quasars that are driving molecular winds. But in a radio mode, the advantage is that it can actually do this to larger distances of several kiloparsecs and even dozen kiloparsecs. So this is a really interesting result that's come out in the last couple of years. Okay, so this is a brief summary of radio mode feedback in galaxy clusters. A lot of what I've been looking at has been to try and understand how is this process evolving with time, and do we see, so we see a lot of radio mode feedback happening in low redshift galaxy clusters, but what happens at high redshift? So is this kind of feedback operating in galaxy clusters for a long time? And if so, what kind of an impact is it having on a long time scale? So most of the studies until I started working on this were focused at low redshift, simply because it's easier to detect these cavities and study this kind of physics in more nearby clusters. At high redshift, it becomes a bit more difficult. But here are some of the results that were obtained. So what we're looking at here is the energy that's associated with cavities. So as this radio jets pushes away the hot X-ray gas, it creates this cavity. You can calculate the energy associated with the work that it takes to move away this kind of gas on that scale. This is what's plotted on the y-axis as a function of redshift. And so you have different cavities here, and we can trace them to quite large and high redshifts, although it becomes much more difficult to see these cavities at higher redshift because you need deeper observations to detect these structures. But overall, what this result shows is that the energy associated with these cavities doesn't seem to vary that much as a function of redshift. There's no significant decline or significant upward turn. The maximum kind of energy that they can provide seems to be relatively constant with redshift. So what this means physically is that it appears that this kind of feedback, this radio mode feedback, seems to have been operating for very long time scales. So over 8 gigayears. This is over half of the age of the universe. And so it does have a really significant impact on long time scales. You can also plot this in terms of another quantity that we use a lot in the field of galaxy clusters. This is called the cooling luminosity. It measures the amount of energy that you would have to inject to keep the hot X-ray gas hot. And so this is the kind of energies that you need to provide to keep this gas hot. And this is the cavity power. So what we're plotting here is the energy of the cavity divided by its time scale. We can take, for example, the time it takes to rise buoyantly up to a certain radius. And what this plot shows is that if you compare the numbers between these two quantities, they're essentially identical in the sense that cavities do have enough energy to keep this hot X-ray gas hot and prevent it from cooling and forming starbursts. And you see that if you plot this for different samples at low redshifts, that's what's shown in gray, versus medium redshift in blue and higher redshift in this kind of orange-red color, you see that there's no significant evolution. The ones at high redshift are not significantly more powerful or significantly less powerful. And so this gives an idea that black hole feedback does seem to be operating quite strongly for many, many gigayears. Okay, so this is what we had back in about 2015. Since then, there's been a lot of work that's been undergoing to understand the high redshift clusters. And I'm going to talk about two examples where black hole feedback does not seem to be working very well. So the first is a classic example. It's known as the Phoenix cluster. So it was discovered by the South Pole Telescope collaboration. What you see here are the central regions of this cluster. At the center of the cluster, there is a massive starburst occurring, which is not what we see in local galaxy clusters, because in local galaxy clusters, radio mode feedback is preventing the hot gas from cooling, and it's preventing these starbursts from happening. But here we have one example where there's a massive starburst. What's interesting about this object is that the black hole at the center is driving powerful radio jets. This is what you see in red here. These radio jets are pushing away the hot X-ray gas that surrounds the central galaxy. And this is what you see in purple here. So the purple color traces the hot X-ray gas. So this cluster is an example where you have quite powerful radio mode feedback. And so what happens here is that the X-ray gas is so dense in the central regions of this galaxy cluster that for the radio jet to actually push away the hot X-ray gas, it takes a lot of work to do this because this region is particularly dense at the center. And so there is radio mode feedback happening, but what we think is going on is that in this particular case, the hot X-ray gas is so concentrated on the central galaxy that even with powerful radio mode feedback, the feedback is not enough to suppress all of the cooling from happening. And in this case, there appears to be still massive residual cooling that's occurring in the center here. So here, radio mode feedback does not seem to be working perfectly well in the sense that it cannot balance out all of the cooling of the hot X-ray gas. So this is one example where we do have radio mode feedback, but doesn't seem to be working quite well compared to local clusters. But there's another cluster that I would like to talk about, which is really interesting. Okay, so what I'm showing here is the mass of many different clusters as a function of redshift. It shows different samples that have discovered clusters of galaxy out to very high redshifts. As an indication here, galaxy clusters, because they're huge structures, it takes time to form them. And typically, we think that the first galaxy clusters, for them to have been virialized and formed, it would be at about a redshift of 2. Okay, so typically galaxy clusters form at about a redshift of 2. So we want to push this sample out to that kind of redshift. It becomes much harder to find galaxy clusters at higher redshift. But here are essentially some examples of different samples, including the one from the South Pole Telescope, which discovered hundreds to thousands of galaxy clusters at high redshift. And the one that I'm going to be talking about is there's this one galaxy cluster, which is located at very high redshift, so about redshift 1.7. It is a very massive cluster of several 10 to the 14 solar masses. It is not the most massive. There are other ones at this kind of redshift that are more massive, but it's among those very massive clusters. And this cluster was discovered back in 2015 by the SPARCS collaboration, which used the red sequence to find galaxy clusters at high redshift. And in particular, Tracy Webb was one of the authors that really pioneered the discovery of this cluster. Okay, so why is this cluster interesting? This is what it looks like in the core. So what you're seeing here is the central regions of the galaxy cluster. This big galaxy here is called the brightest cluster galaxy. It is the most massive dominant galaxy. What you see here is a really interesting feature, which was initially thought to be a tidal tail due potentially to a merger happening in the center. And what Tracy Webb and collaborators found that was really interesting is that they found evidence for a massive starburst happening in the central regions of the galaxy cluster. And so they found that there was a starburst of about 900 solar masses per year at the center of this cluster. But what was really interesting is that this starburst was not located spatially on the central galaxy. It appeared to be offset along this tidal tail feature and very extended. And this was based on Spitzer data as well as VLA CO data, which traced the star formation occurring in this, essentially all of it was coming from this tidal tail feature. And so they said, well, maybe it's due to a merger, a wet merger, and in the wake, in the tidal tail, there's essentially a lot of star formation that could happen. So they went and got CO data, and what you see here is the flux of the CO 2:1 transition as a function of frequency. And so there's a big detection of CO. There's a ton of molecular mass associated with the star formation, about 10 to the 11 solar masses. But what they found was that the emission feature was very narrow. And usually when you see star formation associated in these kind of tidal tail features in gas-rich mergers. You typically see multiple components of the CO or broader component indicating this kind of merger activity. And this was not seen in this cluster. So that's indicated that it's probably not a merger that's driving this star formation. So back in 2020, what we did is that we decided to observe this cluster with Chandra to try and understand a bit more what's driving this starburst. So we obtained 47 hours with Chandra. This seems like a high amount of hours, but this is the kind of exposure that you need to detect clusters at this kind of redshift. And so we got the data, and what you see here in blue is the X-ray emission coming from this cluster. So it's detected, and it's actually consistent with what we call a cool core cluster, which is a very compact distribution of X-ray gas that's very concentrated near the center. And so what I'm plotting here is the density of this X-ray gas of the hot intracluster medium as a function of radius. And typically clusters are divided in two categories, either the blue profiles here, which are galaxy clusters that have a very concentrated amount of hot X-ray gas at the center. And this is where our cluster falls, Sparks 1049 in the black line, versus non-cool core clusters, which have a much more uniformly distributed amount of X-ray gas. Okay, so the X-ray gas appears to be very concentrated in the core of this galaxy cluster, but it appeared to be offset from the central galaxy, which is shown in yellow in this image here. And so we went and looked a bit further. And so if I look at the core of the galaxy cluster, this is the brightest cluster galaxy, the dominant galaxy in the cluster, the very old galaxy. And the tidal feature that we were seeing before is located here where I'm highlighting with my mouse. This is where the star formation is happening. And what we're plotting in cyan colors here in the contours in cyan are the soft X-ray emission. So the low energy X-ray photons coming from the hot X-ray gas. And it appears that these low energy photons are tracing this star formation. So the PSF of Chandra is definitely not as good as Hubble, but consistent with being located on this tidal feature. So what this indicated for us was that whatever is driving this star formation appears to have a link to the hot X-ray gas because they're spatially coincident between each other. And so one idea is that essentially you have a galaxy cluster, you have the hot X-ray gas. If the central black hole in the big galaxy in the BCG here is not in radial mode feedback, then it cannot suppress cooling of the hot X-ray gas. And then this hot X-ray gas would be able to cool and fuel this starburst. And so this is what we think is going on in the system here. So we looked and searched for evidence of black hole feedback occurring in this brightest cluster galaxy. And so we obtained VLA observations of this galaxy. And there is a radio point source associated with the galaxy, but it is extremely faint, not what we would expect if the galaxy was in radio mode feedback. And so in this case, it really appears that you have a galaxy cluster that has this really strong X-ray emission concentrated. It should be cooling this X-ray gas, but in this case, there's no evidence for black hole feedback occurring. And so black hole feedback appears to be failing. And when it does this, then the hot gas is able to cool and form these massive starbursts. What's really interesting about this is that in addition to being the first case where we see no radial mode feedback happening in a galaxy cluster, the amount of star formation that is able to form is really incredible. And you can actually calculate how much time it would take to create the same amount of stars from this star formation as the Milky Way. And it would take about 10 to the 8 years, so only a fraction of the lifetime of the cluster to do this. And this means that it's a very efficient way, this kind of cooling of the hot X-ray gas. It's a very efficient way of dumping stars out to very large distances compared to where the central galaxy is located. And this essentially is one way to build the intra-cluster light that we see in galaxy clusters. And this was the first time that we saw evidence that cooling flows, so cooling of this hot X-ray gas, could actually do this as well. So that was one of the results that I wanted to talk to you about. Now I'm going to focus on another topic that we've been exploring. So I talked about black hole feedback in high redshift clusters, but now I'm going to be focusing on more local galaxy clusters and what we've learned about black hole feedback. And to do this, I'm going to talk about one component of galaxies, which is really important. So here's a cartoon of what we think a galaxy would look like. So you have a galaxy here. It turns out that essentially every galaxy should also be surrounded by a very diffuse halo of gas around the galaxy that extends to much larger radii. This halo is called the circumgalactic medium. We think that essentially this medium is collected through accretion of gas from cosmological scale filaments, where the gas can fall in towards the galaxy. And this gas is really important. The circumgalactic medium turns out to be a very fundamental part of galaxy evolution. Why? Because it contains the majority of baryons associated with a galaxy. And this gas is going to be the main fuel supply for star formation for the galaxy throughout its lifetime. So this gas can be really important for how the galaxy is going to evolve with time, because it contains all of these baryons. So we want to understand this kind of medium, this halo that surrounds these galaxies. The problem is that the halo is so diffuse that it's very difficult to detect with current telescopes. The only constraints that we've been able to have on the properties of this circumgalactic medium have been through stacking of many observations, or through what we call background light sources, where you take, for example, a quasar, and the light of the quasar passes through this circumgalactic medium of a galaxy all the way to our telescopes, and we can use absorption line features to study the properties of this circumgalactic medium. The problem with this method is that although it's very powerful, it only gives very small sight lines of what this material is, and we would like to understand the global properties of this circumgalactic medium. So we've been wanting to study this medium, and it turns out that there is one place in the universe where we can really understand the gas that surrounds the central galaxy very well, and that we can actually detect with current telescopes. And the equivalent of this is in galaxy clusters. So in galaxy clusters, you have the central galaxy, and the gas that surrounds the central galaxy that we can actually see, in this case, it's called the intracluster medium. And it turns out that the intracluster medium, so the gas that surrounds this galaxy here, has a lot of similarities to the circumgalactic medium of less massive galaxies that are not found in clusters. And so we've been trying to understand these properties and how they link to the circumgalactic medium of the more general population. And it turns out that one of the interesting parts is that this gas here that surrounds more isolated galaxies should be highly multi-phase, should contain material that is made of different phases, meaning that it should not only be gas at one single temperature, it should be composed of gas at multiple temperature and multiple phases. And the gas that we see that surrounds this central galaxy here, the intracluster medium, is also multi-phase. And so we've been trying to understand the multi-phase nature of this gas and see how it connects back to the general circumgalactic medium. And so let me show you what this multi-phase gas looks like. So if you take the galaxy here and you put an H-alpha filter on this galaxy, this is what it looks like. So what you see here is the H-alpha emission coming from the central galaxy of the Perseus cluster. This nebula is made of very thin filaments that emit a lot of H-alpha, which traces gas that's about 10 to the 4 Kelvin, so 10,000 degrees. These filaments that we see in pink also contain soft X-ray gas and a lot of molecular gas that traces very cold phases. So it is highly multi-phase in the sense that it contains gas at many different temperatures. And so we've been wanting to understand these kind of nebula that we see in galaxy clusters. But here is the problem with Perseus. So Perseus is one of the closest clusters, so we want to understand it in detail. What I'm showing here is the H-alpha luminosity of this multi-phase gas, and Perseus is located way up here. So it's among the brightest intrinsically, brightest H-alpha sources. And then here is the extent of the nebula versus the luminosity in H-alpha, and Perseus is way up here. Okay, so Perseus is fantastic because it's not only nearby, but the multi-phase gas we see in it is intrinsically very bright and also very large. It's extended to very large radii, so we can understand in detail its properties. The problem is that the nebula in 1275 in Perseus cluster is actually too big. Okay, it extends to about 4 arc minutes in size. And so if you want to fit an IFU on it and understand the kinematical properties of this gas, it's very difficult to do that with Muse or Symphonies. Perseus is also in the north, which makes this more complicated. So past studies have focused only on getting kinematics of this gas on very small scales or through long slit spectroscopy, where you can get an indication of the kinematics here. Now, thankfully, this has now changed because there is a really neat instrument that came online a couple of years ago on the Canada, France, Hawaii telescope. This instrument is called CETEL. It's a Fourier transform spectrometer, which means that for every single pixel in the image, you get a spectrum. And the other great thing about it is that the field of view is really it's extremely large. It's 11 arc minutes by 11 arc minutes. So it covers easily the entire structure that we see in Perseus. And so Perseus was observed in science verification mode because it is so H-alpha bright. And so what do these data actually look like? What I'm going to show you is a little video here of the central regions of these observations. So what you see at the center here is the central galaxy of Perseus. So if I play this video, the first line that you saw in yellow was the O1 line. And then soon we'll see the N2 line across this multi-phase nebula, the H-alpha, and then the second N2 line. Eventually, we have a system which is called the high velocity system, which is a galaxy that's actually infalling towards the central region of the cluster. So it is not related with the central galaxy. And then you have the S2 lines. And so this was the first time where we were able to get the full kinematics of this multi-phase gas. This is what the velocity field looked like. So what was found back in 2018 by my PhD student, was that the velocity field of the structure is very chaotic. It varies significantly from pixel to pixel. So this was interesting. The downside of these data is that since they were taken in science verification mode, we did not choose the spectral resolution of the data. And so what was chosen was actually very low spectral resolution just to test the instrument and see if it worked. And the problem is that with these data, the spectral resolution was about 1800, which is too low and does not allow you to actually resolve spectrally the emission lines beyond the central regions where it's very large, but beyond that, we cannot actually spectrally resolve the lines. So a couple of years ago, we got additional CETEL observations, but this time at much higher spectral resolution, where we were able to resolve spectrally the emission lines out to very large radii. We also got other filters, so you can actually trace the kinematics at other filters as well. And so what I'm going to present to you today are these high spectral resolution observations. The additional filters, we're still working on it. And so I will not show those results today. I will focus instead on the high spectral resolution data. So what you see here is the old velocity field. So this was obtained back in 2018 with the initial data. So we could get the velocity of the gas, but we could not spectrally resolve the emission lines. The new velocity field looks like this. So very similar. So this is at 7,000 resolution. So the kinematics do not change significantly in terms of the velocity. The downside that we have of the data with a high spectral resolution is that it's only able to detect the brightest parts of the filaments. So that's the downside, but we can still see the velocity structure that remains the same throughout the filaments. What really changed was the velocity dispersion. So this is the velocity dispersion obtained in the initial data back in 2018. But essentially what we're seeing here is an instrumental effect. We could not resolve spectrally lines beyond the inner regions. So if we do that with the new data, this is what we find. So this is the new velocity dispersion map, and it shows a really interesting feature. There's this flattened structure in the core of the galaxy, which has a very high spectral velocity dispersion of about 150 kilometers per second. And beyond this structure, everything else appears to have a very uniform and low velocity dispersion. And so if you look at the flux map, we'll see this a bit more clearly. So there's this flattened structure in the core. It looks kind of like a disk, but it is not rotating. And this flattened structure has a very high velocity dispersion compared to all of the rest of the multi-phase gas and the filaments, which has a very uniform and low velocity dispersion. And the reason why this is interesting is that in these regions, we have really active radio mode feedback. We have these jets. These jets should be impacting the surrounding gas. We imagine radio jets as being kind of a turbulent phenomenon that disrupts the gas. But despite this kind of feedback, the gas remains with very low velocity dispersion. So it's very quiescent. And so that's what is really interesting in this system. If you look at the central regions here where we see this flattened structure actually is located right behind the radio jets. So you have the radio jets coming from the AGN, and right behind it, you have this feature here that's really located in the wake of these radio jets. So what we think is going on is that you have a galaxy. This galaxy has a black hole. This black hole is driving powerful radio jets. These radio jets are heating the surrounding gas around the galaxy, but they're also, we think, triggering small instabilities that cause some of this gas to condense and cool. And if essentially as it cools, it becomes denser, and as it becomes denser, it will fall towards the central regions, feed the black hole, reignite the cycle. And so we think that there's this loop going on. But what we also see is that when it triggers this kind of multi-phase gas, it appears to do this in a very quiescent, non-turbulent way. And this is what we think is explains this low velocity dispersion that we see in the outer filaments. Whereas in the wake of these radio jets, simulations show quite clearly that when you have these radio jets, in the wake of them as they rise buoyantly, you can have a lot of turbulent motion. And in this turbulent motion, this is what we think is leading to this very flattened structure that has a high velocity dispersion, and that's located in the wake of these radio jets. So we think that these radio jets may be triggering this multi-phase gas, this formation of multi-phase gas in a more turbulent way. And if it does this, it appears to be really localized to the wake of these radio jets. Versus another mechanism that leads to the formation of this multi-phase gas. But what's really interesting is that it appears that this process has to be very gentle, very quiescent, and to be able to explain a very uniform and low velocity dispersion. So that was what we saw for Perseus. We also compared the kinematics that we saw of the multi-phase gas of these filaments to what we see with Hitomi. And so Hitomi was an X-ray telescope that was able to observe Perseus before it had a catastrophic failure. Soon there will be its successor, Prism, that is scheduled to be launched in a couple of months. But Hitomi was able to observe Perseus and get the kinematics of the hot X-ray gas. And if you compare what Hitomi found for the velocity dispersion of the hot X-ray gas, so if you look at region 0, which is located in this rectangle here, so Hitomi, the downside is that although it has fantastic spectral resolution, its spatial resolution is not good. So we can only get the constraints of this region here. And if we take all of the H alpha gas that we see, this multi-phase gas, and we look at the velocity dispersion of the multi-phase gas seen in H alpha, it's very similar to the velocity dispersion seen in X-rays. So this seems to be indicating that the kinematics of this X-ray gas and this H alpha gas are connected, that if this gas forms from cooling of the hot X-ray gas, then this process of cooling from very hot temperatures down to about 10,000 degrees, where we see H alpha, is connected in this process. You can also compare this to Herschel, which saw a much colder gas. So again, Herschel was able to observe Perseus. Its spatial resolution is not as good as what we see in H alpha, but you can still see how the velocity is actually very similar between the 10,000 degree phase and the 100 Kelvin phase. So what I'm plotting here is the velocity field, and I'm using the same color bar, and I'm highlighting just different regions here to show that it's very similar. So the kinematics of the 10,000 degree gas appear to be very similar to the ones at 100 Kelvin. So there's really a connected structure between how gas is able to cool from X-ray temperatures down to the H alpha phase, and even colder down to the molecular phase. So that was for the multi-phase gas that we see around galaxies. Now I have a couple of minutes left, and I want to talk about one of the pieces of work that we've been working on in the last year or so. And this is really geared towards what's coming up in the future. So I'm going to show you a glimpse here. So I talked about Hitomi, and I'm going to show you here just how fantastic Hitomi was. So again, Hitomi was this X-ray telescope, which was able to observe Perseus, and if I remember correctly, just one other source before it had a catastrophic failure. What you see in white here is the spectrum that was obtained for Perseus. Hitomi has a really fantastic spectral resolution, and so you can see a lot of emission features. In red here was the previous best spectrum that was obtained of Perseus. And as you can see with Hitomi, we see many more emission line features, a lot more physics that comes out from the spectrum. And so the successor of Hitomi is scheduled to be launched in spring or summer of this year. So we should be able to get more observations. But what this showed us, and what this indicated, at least for my team, was that we have the opportunity of really looking at spectra, X-ray spectra, in much greater detail than was before. And so we decided to see what else can we learn about these spectra, and in particular using machine learning. So machine learning really has just had, an incredible amount of work that's been done in the last couple of years in astronomy. The reason why machine learning is so great for astronomy is because in astronomy, we have a lot of data. We actually have too much data, and it becomes really difficult to analyze these data given its quantity. And so people have been using machine learning to do this more efficiently, quicker, and sometimes even more robustly. So there's been a lot of work on galaxy clusters, but until now, they focus on imaging. So can you use machine learning to learn something more about the images that we see in X-rays? What we wanted to do was to look at the spectra that we see in X-rays. But here is the problem with X-ray spectra. What I'm showing here is a typical spectrum that you get for a galaxy cluster in X-rays. So this is what you typically get for any kind of typical cluster at a certain temperature, certain metallicity. You would get this kind of observation. And actually, this spectrum that you get is not the real spectrum of your source. What happens is that the observed spectrum that we obtain is actually a convolution between the response matrix of your telescope and the true X-ray spectrum of your source. And what happens is that when you do the convolution, it actually washes out a lot of the emission line features that you see in your X-ray spectrum. So the spectra that we are working with usually are the result of the convolution. And ideally, what we would want is to recuperate the true spectrum. You can convert this, this integral into a matrix equation where you have the true spectrum and then the response matrix in the form of a matrix. And mathematically, it's actually really difficult to invert this and be able to extract your true spectrum from your observed spectrum. We tried several mathematical techniques and we published a research note on this to show that it's actually mathematically very difficult to do this inversion. And it does not work when you have complex spectra like the ones we see in galaxy clusters. So instead, we said, well, is there another way of inverting this spectrum? And it turns out that there is a neural network that was specifically designed for deconvolution. And this network is called a recurrent inference machine. So this was first published in 2017 by computer scientists. And I don't think they realize that in astronomy, we have many convolutions and deconvolution problems. And so when they published this, there was one group that right away used this technique, this neural network for deconvolution, to deconvolve ALMA images. And so they did this successfully for ALMA images. But we asked ourselves, can we actually do this for the X-ray spectra that we have? So a recurrent inference machine is just a type of neural network that's made of convolutional layers. These convolutional layers extract the maximum amount of information of your spectra, and they discard any information that is not relevant for the deconvolution. And then you have the recurrent units here, which learn to map this equation where you have the observed spectrum, which is the result of the response matrix convolved with the intrinsic spectrum. And so they learn this mapping. And then once you run your recurrent inference machine and train it, then you're able to apply it to your observed spectrum and deconvolve the spectra. So this is what we've been doing with the Chandra team at CFA, trying to develop this technique to deconvolve. And here is just an example of what we get. So what I'm showing here is an observed spectrum. And I'm almost done here. And then you have, this is the true intrinsic spectrum seen in orange colors here. And then if we take the observed spectrum and run it through our recurrent inference machine, this is what we get in blue colors here. So the recurrent inference machine is capable of deconvolving the X-ray spectra that we get. And why is this interesting is that if we recuperate the true intrinsic spectrum, it turns out that when you fit models to this spectrum, you can actually get better constraints on your parameters because the model relies heavily on the emission lines that you see. And by recuperating more of these, it seems to be able to get better constraints to fit more tightly the parameters. Once you get your true spectrum, you can also stack spectra from different epochs. You can see how X-ray sources intrinsically evolve as a function of time without the influence of the response matrix of the telescope. And what's interesting is that you can also use a calibrator. And since a calibrator does not evolve with time, you can then apply the recurrent inference machine to your calibrator. And if it is not finding a constant spectrum for your calibrator, this means that the calibrations that we have for the response matrix are not perfect. And we can actually use this method to better constrain the response matrix of X-ray telescopes, in particular Chandra, because we know that it's been degrading with time. And so we're working on this kind of project to get better calibrations. And so this finishes presentation. So I'm just gonna quickly highlight some features here. We've been developing machine learning tools for X-ray spectroscopy, looking at black hole feedback in distant clusters. I also showed some really neat results that we've been able to obtain with CITEL, which is really a fantastic instrument to use. And I will take questions now. So thank you.
Thanks, Julie, for a very, very exciting talk. Any questions? If the participants online raise your hand, I can see it. For those in the room, Will, you can just conduct things in the room.
We have a question from Nayesh.
Hello, a very nice talk, Julie. Can you hear me?
Yes, I can.
I'm curious, the problem with machine learning is, of course, the training set, and you're training it based on a set of a spectra that you expect for, I guess, some theoretical galaxy clusters, but those theoretical galaxy clusters may not be like the ones that we have in the real world.
Yeah. So this is a great question. Okay, so first for Tetra and for XMM, I think we have a good enough understanding of atomic databases to be able to simulate the spectra of galaxy clusters pretty well. This kind of problem really becomes interesting when we try and look at Hitomi spectra. So Hitomi, one of the key features that was super interesting is that it showed that there's a bunch of lines that we didn't even know were there initially. So our atomic databases were not robust enough. And so now it's become much better from what I've heard. So they should be able to simulate more robustly. But we've been also looking at techniques to include in the simulated spectra some unknown features that could be there. So we can add just like Gaussian variations to account for other lines that we don't know are necessarily there. So we are exploring this. I do not know if it's going to work, but it's something that we've been thinking about, especially for Hitomi and Prism that's coming soon.
If I can follow up on that. I think the issue I'm particularly worried about is this temperature distribution that, usually I assume that there's a single temperature gas that emits the...
Yep.
And in reality, there could be distribution of temperatures,
Yeah, so this is a great question. We actually have another paper that looked at this kind of aspect. You can actually simulate including multiple components of different temperatures. So you can include this in your training set quite easily. I just want to show here one key part. Let's see. Yeah, so we have another paper which looked at specific regions in galaxy clusters. You have an X-ray spectrum here. It can actually be made of a plasma that's at one temperature, that's a combination of two temperatures or even more. And so in your simulated data, you can include not only one component, but multiple components. So this is something that we're doing, yes. So it can account for that.
Hi, Julie. That's a wonderful talk. And I know the feedback, the study of the feedback procedure is always focusing on the distant clusters. And how about our local clusters? So what do we know about, for example, can the study of the local environment tell us, for example, if there's a jet of steady star or not, or what it can tell us if we apply the same procedure to our local galaxy?
Would it be possible to maybe Will to repeat the question?
Sure. Okay, I can repeat. So basically, I know the entire study for the feedback is focusing on the distant galaxies, and my question is, can we apply this method to our local galaxies, to our local cluster? For example, can we study the local environment, the hot gas around our galaxies, and can this be applied to tell us anything about the potential jet of Sagittarius star, or if there's a jet?
Okay, so in local clusters and galaxies, there's been a lot of studies that have done this in quite a lot of detail. So like Perseus is just one example, but it's actually not the nearest cluster. So you have Virgo, for example, where we also see this kind of radial mode feedback. And Virgo, what's really interesting is that it's nearby enough that you can resolve really like down to the core what's happening with these feedback processes. So I know Brian's worked on that. I know like Helen Russell, who was at Waterloo, worked on that a lot. So we do see in great detail in local clusters. I would say it's more the high redshift systems that are much more difficult to see. So I don't know if that answers your question.
Yeah, and the follow-up is because we do not see a jet for Sagittarius star up till this point. So, and what's possible reason for the quenching of star formation rate in Milky Way, for example?
Yeah, okay, so Sagittarius A star, super interesting system. My understanding is that it's still debated if like the Fermi bubbles are actually from radio jets versus like star formation episode. My understanding was that it's actually pointing to more of a radio jet's origin. So there might have been a radio jet in the past. There currently seems to not be, but currently the accretion rate of Sagittarius A star is about 10 to the -7 Eddington, if I remember correctly, which is much lower than what we see in these systems here. It's about 10 to the -4. So these are black holes that are a bit more active. Maybe Sagittarius A star eventually will be a bit more accreting a bit more, and then we'll be able to power these radio jets. So it might be related to that too.
Thank you.
Thanks, Julie. The filaments in Perseus, what is exciting the H alpha? Is it coming from star formation, or is it shocks in the cluster, or what actually causes that H alpha emission?
Yeah, so this is a great question. I don't think we have a definitive answer. So it is not star formation, that's for sure. If you look at star formation happening in here, there are clumps of star formation, but it cannot account for the entire H alpha that we see. And the spectra of these H alpha are really not what we see normally associated with star formation. So the N2 line, for example, is brighter than the H alpha line. So it appears that to be able to explain them, you need some kind of high energy particle that could be interacting with these multi-phase gas. It could be the particles coming from the hot intracluster medium because they're everywhere. So that could be one of the particles. It could be those coming from the radio jets as well. So it looks like there is some kind of energetic phenomenon that you need, but my understanding is that what that is exactly is still not clear. And you do have some shock fronts, and you do see some changes in the emission line characteristics along the shock front, but not like throughout the system.
Thank you.
Hi, Julie. Thanks for the engaging presentation. I just have one quick sort of naive question about one of the figures you showed us. Can you just go to the slide right before you started showing off the Sparks field?
Yeah.
About the figure. Yeah, so that sort of big figure. I'm trying to understand why it seems like got the largest clusters. It seems like the mass of those clusters peaks at around redshift 0.2 before it drops off when you look at the Planck sample. Is there any particular reason why it tends to peak not at redshift 0, but at redshift 0.3 or so? Or
Yeah. So there are many like effects that is driving kind of this peak here. So first of all, very massive clusters it takes time to build them. So the 10 to the 15 clusters that we see today will not have existed at redshift 2. So that's the kind of increase that you see here. And then here, what happens is that a 10 to the 15 solar mass cluster is really rare. Like these are huge structures and they're just rare. So we don't see a lot of them nearby. So those features there that influence both kind of this part and then this evolution here too.
Okay, I think that's it for questions in the room. Are there online questions?
Yeah, I don't see any online, but I have a question.
Yeah, go for it.
So I was just gonna, well, it's more of a comment on understanding that where you mentioned that flattened structure in the center of Perseus, and then further out the which has higher velocity dispersion, and then the lower velocity dispersion stuff to north and south. I mean, one thing that might help to understand it is, you know, excuse me, the difference between jet and lobe dynamics. So in fact, when you show the radio source, you know, 95% of what you're showing there is actually the lobe and not the jet. The jet is just way down in the throat, and it's disrupted by the time you get on that large scale. So that radioplasma that you're seeing there, like the bubbles, are responding to buoyancy, which, you know, so rather than moving at, say, a large fraction of the speed of light, they're moving at a significant fraction of the speed of sound there, you know, and so that, you know, that will contribute to perhaps, you know, the gentle dynamics that you see, because the stuff will be pulled up, you know, in some cases in Perseus, maybe in a laminar flow, which has, you know, is linear and may not have a large, you know, lateral velocity dispersion. Although when you observe, we're seeing it, of course, along the line of sight. But that might help to sort of understand the difference in those dynamics where, you know, things are much more turbulent on the inside and more quiescent on the outside.
Absolutely, that's a great comment. There is a paper that came out by Irina and her group, Irina Zurevleva, who's at Chicago, and I don't know if you were on that paper, but they had bubbles. So they simulated bubbles that were already formed. So they did not, you know, take into account how these structures get there. But let's say once you have a bubble and then it rises, what happens? And they do have some turbulent flows that develop in the wake. So our understanding was this could account for what we're seeing in the flattened structure. But as you say, in general, it's much more gentle feedback than the explosive kind of jet feedback that we see in other simulations. Yes, thank you.
Yeah, the simulations generally are pretty lousy at doing this. So I shouldn't say that too loud because I'll piss off many of our colleagues, but they just don't really match reality very well. So not the best place for guidance. Okay, any other questions? I guess we're pretty much at the end there. If there are no more questions, please speak up or hold your peace until the next time Julie's here.
The smell of pizza has got to everybody.
So is that, are we good then? Any more questions?
Yeah, we're good. We're good.
Yeah, okay. Well, let's give Julie another warm hand.
Thank you. And sorry again, I
so much. That was really, really a very nice talk, and I hope your travels go well and your family gets over their stomach flu quickly. So thanks.